presenting our swarm intelligence case study.
Hello everyone, I'm Nicholas Craig. You can see my name up there for your evaluation sheets. I'll be talking today about swarm robotics. This is what I've been focusing on for my research project and hopefully what I'm going to help you guys learn a bit more about today. So, this presentation I'll be going through an overview of what swarm robotics is, what some of the principles are, how it works, talking about benefits, limitations, applications of these approaches. And then the fun part, I'll be doing a demonstration of my research project that I've been working on, thanks to this being week 11. And then I'll wrap that up with talking about some of the issues I attempted to address and what the future of this research field looks like it could be. So firstly, what is swarm? There's a lot of terminology floating around. You can talk about distributed artificial intelligence, multi-agent systems. A lot of these areas have the same sort of core ideas behind them. And the idea is that rather than build one system, one massive, huge, monolithic system that is capable of doing anything and everything that you throw at it and coming up with the entire solution, it's in some cases easier to build lots of small systems which each have a part of the solution and which, when those systems work together, can produce that solution with overall less hassle and less complexity and less time spent developing and testing. Swarm robotics is exactly that. Rather than building these really big, complicated robots that can walk and run and climb stairs and shake hands, we build smaller, simpler robots. We build small, self-contained robots with decision-making capabilities, sensors, and some ability to manipulate or work in the world. And we get them to coordinate their actions and cooperate to achieve something a lot more than the individual robots could. So that's sort of the idea behind swarm robotics and the idea behind the approaches. Some of the benefits of these approaches are you get a lot of flexibility with your solution. You can divide your resources in a way that you can't when you're only using a single system. Smaller problems only need a smaller number of robots applied to them. Larger problems can have more robots all jump in, and you get flexibility in how much resources you allocate to a particular problem. To develop these robots, it's also cheaper and simpler. Rather than developing a robot that has to do everything, you just develop lots of robots that each do one thing. And that can be a lot simpler. And you also get redundancy. Now, while you might think redundancy is a bad thing, when you've got 10 robots, 6 of them can break and you can still get the job done. If you've only got one system, as soon as that system falls over, you got nothing. So you get a lot of flexibility and you get the ability to continue even when individual modules fail or break. Some of the limitations particularly during development, is that it relies on emergence. It can be quite confusing to try and stick these systems together and predict what they're going to do at the other end. There's also a different set of development skills that you need. I've come across really, really weird debugging problems trying to chase which agent said what to which other agent, which upset it and caused it to cry in the corner. And also finding scenarios that this is applicable to. Yes, it's something that's still, because it's a new research field, it's something that's still developing. We still haven't quite got our legs under ourselves to know exactly what scenarios we're really good at and what scenarios other approaches might be best for. So what are some of those possible applications? Obviously, if we're dealing with robotics, anything that's happening in a hostile environment. So we can send these robots into radiated environments, we can send them into subways where we don't really want to be, we can get them to do things like exploration, we can get them to do maintenance on systems and hardware, we can get them to do manufacturing, and we can get them to do harvesting, whether that be agricultural or in the mining industry. These are some of the things that these robots can be applied to. What I'm going to talk about now is my research project, now that you guys have a little bit of an understanding of what swarm is and what it means. My research project was to create a swarm simulation for a specific scenario. We had someone mention whatever's happening on Mars at the moment. I didn't know about that, the Mars rover. My scenario is an extraterrestrial landing, be it Mars, be it Europa, be it Kepler even. And what I'm trying to show here is how swarm robotics can provide autonomous and independent solutions, autonomous agents that can go and work and do their thing. That can be a cooperative robotic team, meaning that they can utilize the resources of their fellow agents, and with the goal of exploring the planet, collecting scientific data, that sort of thing. So now it's demo time. So here we go, planet landing. This is the simulation, and this is the surface of the planet. It is a bit hard to see, but that's okay. The grey things you can see are rocks. These are things that the team is interested in, and the little red flags are resource spots that I've generated into the world that the swarm would want to act on. What you can see in the middle, that white thing, is the shuttle. So we're on the planet, our shuttle has just arrived, it's set down and it's landed, and the operation is about to begin. In my scenario, the shuttle has a few key features: the ability to process these rocks, in future the ability to recharge and repair robots, and forming the main sort of hub where communications about the swarm and about the data collected would then go off planet. I will have a note that the hub, the shuttle, while it is in the centre, it is in no way responsible for task delegation, telling robots what they need to do. It just sits there, and in fact currently it doesn't talk to the swarm at all. That has yet to be implemented. So I'll skip ahead to about here where stuff starts to get interesting. What's happening now is the shuttle will start dispersing the first type of robot. What you see, these blue things moving around, these are scout robots, I've dubbed them. These are highly mobile. These have very advanced sensors, very large visual range, as seen there, and they have communication ability. So the jobs of these robots is to go out, explore the environment, see what's going on, decide what needs to be done, or pick up things that could be done, and then communicate via these communication networks that they build that information around to all of the other robots in the swarm. So these robots can't actually manipulate anything inside the world, but they provide a very important resource, which is information. We skip ahead a bit more to here, and we'll see our next type of robot. This type of robot is the Move robot, or MoveBot. Lot slower, lot smaller vision range, nowhere near as sophisticated sensors, but it has the ability to actually move and manipulate things within the world. What these bots are doing at the moment is going out, finding all those rocks that the scouts identified, and collecting them. Much smaller visual range. Collecting those rocks and piling them towards the hub where they will get processed and analysed for scientific data. And these are the communications that the robots have with each other. So all of the information gathered by those scouts can be spread to other scouts and spread from scouts down into different types of robots. And we'll see that these robots, they can move things around, they can push things, they're mobile, they can deal with difficult terrain. Theoretically, a lot of research has gone into that. But what they can't do is they can't do anything more complex. They can't work on these resource fields, they can't dig at those flags which have been identified. All they can really do is push other objects around. So what we need to get that job done is another type of robot. You can sort of see them spinning out in the centre, they'll move out in a second. These robots are task robots. These represent robots that have specific hardware designed to deal with specific problems. In this case, drilling equipment, meaning that these robots can drill at certain locations, dig up rocks, dig up resources that can then be moved around. A limitation of these robots is that these robots can't move themselves around. It's complex enough trying to build autonomous drilling equipment, let alone trying to get it to be able to move and navigate around. But we've already got robots that can move around, so we'll get them to push us where we need to go. See, we're dividing those responsibilities between our robots and making each robot very focused in its task and a lot easier to manufacture, design and build. So what's happening again is the same way that the movement bots were informed of the rocks that needed collected, the task bots are being informed of the places that need to be drilled at. And we can see that the movement bots are pushing those task bots around, they're requesting the assistance of other robots, they're getting that assistance, and they're able to do their job. What you'll also notice is that because there's a group of robots rather than a single robot, they can do things in parallel. We can have 6, 7, 8 rocks being collected all at once. We can also have a great deal of redundancy. I think they're about to derp out. These bots all here, they've all jammed up, but that's all right, because we've got other robots. So even though those particular robots are frozen or jammed up or are having an argument about which way to go, the swarm as a whole can still move on, it can still process, it can still complete whatever task it was set. So that's the prototype I've developed. There are a few things still that I want to include. I want to simulate battery life and have solar robots actually power the other robots, and maybe even model hardware failures so that when robots break down, other robots can go and retrieve them. Because even though the idea of the swarm is to have multiple agents, if one breaks down it's okay, not many researchers I've seen have actually gone into how do we recover that robot. It's still a resource that we need. How do we fix it, or how do we get new robots into that system? So that's my simulation. I hope you thought it was cool. I have a question, yes?
When you were just showing the movie robots pushing the rocks around, I see one brother pushing the rock, another one coming and taking that rock away and actually pushing it towards the car while the first one goes and pushes it as well. It's just accidental because just second one bumps the rock, or is it kind of like a conveyor belt where they move rocks from one to another?
So that's very interesting. That's not something that I've explicitly programmed. He's talking about robots conveying rocks. So I'll push the rock this far and then someone else will take it and push it further. That's not intentional. What's happening there is a robot's pushing a rock, it's getting stuck, it's turning or something, and simply because there's another robot that knows that rock's there, if he can push it further, he'll go ahead and push it. And once that rock leaves the MoveBot's vision range, he sort of loses that task and says, oh, well, I'll do something else now. So that's completely emergent behavior. And it's fantastic that that particular behavior emerged and was useful, rather than emerged and was really weird, like bots freezing up. Cool, so just to talk a little bit more about the issues I tried to address. A lot of these papers and stuff that I've been reading had some very weird ways of approaching the problem. I've listed these as an isolation fallacy. A lot of them seem to be so focused on simulating ants and bugs that they don't realize that with the internet and all of our ways of communicating and realizing how powerful and useful communication is, why are we limiting our designs to not being able to communicate? So isolating your modules doesn't make as much sense. Identical agent fallacy. There have been a few papers I've read that say all the agents must be the same. But if all the agents are the same, then as soon as one needs to do something specific, there's no hardware that can deal with it. If you've got a whole bunch of robots with tracks, they can't undo screws. You need a specific hardware for that. And vague goals and scenarios, it could just be the papers that I've read, but a lot of the research seems to be, we know this is cool and we know it could be useful, but we're still trying to figure out exactly where it will be useful. So I tried to address some of these problems with my application. What are the future of swarms? Where are they being used? Where could they be being used? What needs to happen? I believe that as we go on, standards will be established. What works best in what scenarios, how to do it, and we'll get these pathways that future developers can come along and follow, meaning that we know what we're doing, basically. Solving common robotic problems. This is more of a robotics and engineering field that I'm not as familiar with, but once we know how best to get a group of robots to move around rough terrain, that can be no longer a research project on its own, but the cornerstone of future work. And human swarm interfaces. It's great that we can get these things to go off and do their thing, but if they're doing the wrong thing, we don't want to have to take them all back to the lab, pull them apart and change their code to tell them that that's the wrong thing. We want to have some sort of interface that we can use to communicate with them. Some other interesting technologies that might relate to these. AR drones, obviously flying robots, fantastic. Non-rigid robots, there's weird robots I've seen that are powered by air pressure and memory foam alloys and stuff like that, so that could be very interesting. They've also got potential applications in emergency response scenarios, obviously in the military, and in home convenience. And this is just swarm robotics. Yes, this is just swarm robotics. The actual design ideas behind building the software that works in this way is already being applied. It's in business expert systems, it's in manufacturing, production lines, and all sorts of stuff like that. So the ideas are shown to work, it's just finding the robotic applications. So this is swarm robotics, the idea that, much like people, much like insects, much like a lot of things that we see, one solution or one massive solution might not be the idea. What the best thing might be is lots of smaller agents that all have a part of the solution, and working together they can be a lot more than any one of them could be individually. Thank you.